So, we have discussed the additive drag. We have also discussed the decol that was just proportional to Mach square, to the flight Mach number square here. Just a small comment related to this the additive drag. This small comment I want to give, this is that, of course, when you increase the Mach number, this is always going up. And when you are at supersonic speed, this is much increasing. What is the reason? You will have a shock, for example, a shock that is here. What is happening through a shock? You have an increase of the static pressure. The total pressure is decreasing and the static pressure is increasing. So that means that you have a P here that is much higher. Due to the shock, due to the presence of the shock. And if this P is much higher, when you have a shock, when you are flying supersonically, the additive drag is increasing a lot. So the problems, let's say, related to the additive drag are always existing. You must absolutely consider them, but if the aircraft is a supersonic aircraft, then it is even more important. And so all this theory behind the additive drag, the lip suction thrust, the cold drag, the nacelle drag is extremely important in function of the Mach number. You see also if here the Mach number is higher than 1, so the decol will also increase a lot. Okay? Now, what about the lip suction thrust here? The lip suction thrust, this is much more difficult to study theoretically than the additive drag. Why? Because the way to proceed, this is to consider an intake that is in a flow with, of course, the subsonic part here, but we are not considering this part because we have already studied this part in the additive drag. And you have a flow that is flowing at a speed VA here, and of course that is leaving the system at a speed V1 that is smaller than VA, but here around you are also passing with a speed, let's say VA, or maybe a bit different than compared to VA, but much related with VA. And if you want to apply the theory of the impulse, so the theory of the impulse or the quantity of movement, you need to put a surface here that is far away enough of the system so that everywhere around the system you will have here the pressure PA, here you will have 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 the pressure PA, and here of course you will have the pressure P1 that is higher because you have reduced the speed compared to PA. And maybe also in the center here you have this famous spinner that you need to consider, and of course V1 then it's on the around side of the spinner V1. And if you apply the theorem of the quantity of movement, the same as the one we have seen before, to this system, what will you be able to compute? You will be able to compute the force that you have, let's say, here on the surface, and maybe there is also a force here on the spinner. Okay? And of course, if you integrate that over all surfaces, this force is one force over the surface that is, let's say, negative, that is null, that is 0 in the vertical direction, because this component here is compensated by this one, but you will have, globally speaking, a force that is going in this direction, and maybe a small force coming from the spinner, or you can draw it like this. And you will obtain, indeed, a force. But it's not the lip suction thrust, because the lip suction thrust is only the force that you have here. It's only the force that you have there. And by considering the system that you have taken, you have the force on this surface, but also the force on this surface, the force on this surface, and the force on this surface. And the red forces that I have shown here, these ones, they are already included in the thrust. So you have computed a force that is containing, so the green one plus the red one, and there are two red ones, because there is a very small one due to the spinner. This is something that is the lip suction thrust plus something else, because you have computed the lip suction thrust and you have computed that. This is one force that you have containing the lip suction thrust, but also containing a certain percentage of the thrust, in fact. Because this is a part of the thrust, this is a part of the thrust, this is a part of the thrust, and you obtain something else than the lip suction thrust, something higher than the lip suction thrust, because you are including this and that. This is what, if you make a computation like this is what is called the T entry, TE or T entry. T for thrust, thrust of the entrance, of the entry part of the intake. And there are theories, they are developed in the notes. I have not yet put the notes on the UV or on Toledo, but I will put them. And you don't need to look at that really in the notes, but you can compute this. There are equations that are enabling you to compute that, but this will not be the lip suction thrust. This is higher than the lip suction thrust. And of course, with this, you can also introduce a CTE, like we add the CD additive, you will have a CTE. And you can, of course, also introduce a C lip suction thrust, which is a non-dimensional coefficient of the system. And of course, you should be able also to define, to prove that the C lip suction thrust, as well as, but it will be another function, as the CTE, they will be function of the Mach number, AA divided by AI, but also, of course, you see, they are depending on the geometry. And so, that is also why we are less keen to spend a lot of time on the lip suction thrust, on the T entry, on the CTE, on the CLST. This is because your rationale will change with each geometry, because they are not a unique curve like this one. They are not a unique curve like this one. They are a curve that is changing for each intake. Not each intake of the same aircraft. In function of the aircraft, a Boeing 737, a Boeing 777, an Airbus A340, an F-16, an F-15, a Rafale, they will all have a different LST. And globally speaking, when you add the D additive and the lip suction thrust, you will have a drag. So when I say I add, this is let's say, positive when I say that. This is negative, and so the result will be positive, so it will have the same sign as the d-additive. And this is what we call the spillage drag. This is the sum, if you want, the combined effect of the additive drag and the lip suction thrust, the spillage drag, okay? And of course, you can also introduce a CD spillage, that will be also function of Mach number, AA divided by AI, and of course also the geometry. So as the lip suction thrust is depending on the geometry, and the CD spillage, you will define that as the D spillage, which is the sum of these two, each one containing its sign. So one of the two is negative, one of the two has another sign compared to the first one, divided by something with 1/2 rho v square and a surface. So which v square, of course, it will be VA square, which rho, it will be rho A, and which A, it will be AA. Okay? And if you have an intake, I will show you a few examples in some extra slides I will add on Toledo and on the UV. For each aircraft, you have, as you have the CL and the CD0, you have the CD spillage curve. You have the CD spillage graph of a given aircraft, which is in fact the CD spillage of its intake. Okay? And you will find for each aircraft the CD spillage in function of flight Mach number, AA divided by AI, and the capture area ratio. I remind you the name of this, capture area ratio, and for this aircraft, the given geometry. And you must be very careful because it's maybe something that you have already seen, but if you take Boeing 777, for example, they don't have all the same intake. Depending on the models, depending on the engine that is installed, because you can put a Rolls-Royce engine, for example, or Pratt & Whitney engine. If you put a Rolls-Royce engine, the intake will not be the same as with the Pratt & Whitney engine, for example. And so that means that this aircraft can have two CD spillage curves, one for the intake going with the Rolls-Royce engine and one for the intake going with the Pratt & Whitney engine. But each of these two curves for this existing aircraft is depending on this geometry and will depend on these two parameters. Now this is the CD spillage. And the CD spillage is something leading to a spillage drag because the additive drag is larger than the lip suction thrust, each one including its sign. And on top of that, I remind you that you need to add the coal drag. So you see that